Welcome back. Today we'll look at paper 1 variant 13 of the October-November 2023 series. Now they give you 1 hour 45 minutes for this paper. Hopefully I'll be a little bit quicker, although the video will probably be quite long. So I would recommend watching at 1.25 or 1.5 speed. And rather than just watching this video, make sure to also check the mark scheme, because while I might give 1 or 2 answers, the mark scheme might have 3 or 4 answers. Right, so if we look at question 1, it says a mobile telephone has a built-in input and output devices. Give 2 examples of input devices that would be built into a mobile telephone. Right, so input, one we can just say touchscreen. And then I guess we can also say, let's just say like microphone. Alright, but for these you can also think, well, there's going to be a camera, possibly there might be a keyboard. Right, you can also say things like accelerometer. And if you don't know, an accelerometer, well, this is what's used to measure the acceleration of a phone. And with the acceleration, this can be used to measure the rotation. Right, so let's say your phone is in portrait mode like this. Right, if you suddenly switch it to landscape mode, well, the accelerometer is what's used to detect the phone's rotation. And then of course it will then flip the screen up, likewise for maybe a car racing game, something like that. Right, so B, give 1 example of an output device that will be built into a mobile telephone. Here we've said touchscreen, so I probably won't say that again, right, although I think you probably could say screen. Here let's just go speakers. And I think if you forget these, I think one good bit of advice I would give is think of the senses. So one sense, right, touch, also sound. So if you think, well, what's an output device, think, well, how does a phone output sound? How does a phone output light, right, obviously for vision. So just think about those kind of sensors, right, things that humans can detect, and then think how a device would either input that data or output that data. Right, the data storage in the mobile telephone can be measured using different units of measurement. State how many bits are equal to a byte. Right, so this one should be easy, just 8 bits in a byte. Now, possibly they might ask, right, what's 4 bits? And this one is probably a bit more difficult, but 4 bits is actually called a nibble. And the reason it's called a nibble, I think basically it was just a joke. Right, because if you think of like an animal, well, a bite, right, that's a big bite, right, maybe they're eating a big meal. But a nibble, where you say this is a small bite, right, so maybe you say like the lion kind of bite, or right, the lion bit the zebra, but maybe like the mouse nibbled on cheese. So a nibble is just a small bite. Right, so then we want to state how many kibibytes are equal to a mebibyte. Now this one, hopefully you know the difference when it says kibi. Well, this means 1024, right? Whereas when it says, kilo, mega, giga, right, tera, well, that means like 1,000, and then obviously, well, a million, a billion, a trillion. But right, in this case, well, 1024 kibibytes equals a mebibyte. And I do actually have a picture here for this one. So what we can say is, well, 1 kibibyte is going to be 2 to the power of 10. Right, because 2 to the power of 10 is this, right, 1024. Right, then if we look at mebi, well, mebi is then 2 to the power of 20, which I guess, is this value here. Right, gibi, 2 to the power of 30, tebi, 2 to the power of 40. So the pattern you see, of course, where the power just increments by 10, right, 10, 20, 30, 40. And because if we think like power laws, right, laws of power, then well, kibi is going to be 1024 bytes. So that means that mebi is then going to be 1024 times 1024. Okay, because well, 1024 is 1024 is 2 to the 10. Right, then if we times those together, well, 2 to the 10 multiplied by 2 to the 10, right, equals 2 to the power of 20. That's just the power laws, right, in maths. And then of course, well, then we go, times 1024, right, that's going to be, that's going to be this one here, right, this gibi. Of course, another 1024 is going to be the tebi. Right, so then we want to describe the purpose of an operating system. And I think for this one I'll type Right, so I think an operating system, I mean, the first thing we can say is going to manage the hardware. And as always, okay, I'll just write in bullet points, but in the exam, you should write in sentences and paragraphs. So let's say maybe manages hardware, and maybe and allocates resources to processes. Because let's say you open some process, right, open a program, then that program will want to use the CPU, right? That program might want to use, the network card. It might want to be saving things to disk, loading things from disk. Maybe it wants to use the GPU. But of course, we can't have one process that's, maxing out 100% CPU usage, right, or 100%, GPU network usage. So it's going to be the operating system's responsibility to, fairly allocate the resources among all of the processes. Right, so I think that's fine. And then we can also say it's going to provide maybe we say it provides a way for the hardware and software to interact. So kind of an interface between the hardware and software. And I then want to say, well, it also provides an interface, let's say between the user and the hardware, or the user and the system. So I mean, we could kind of combine that as one point, but probably let's make it separate. So let's go provides, maybe provides user interface, for user to interact with the system. Let's say sort of hardware / system. Right, and I mean this user interface, again, it could be, command line interface, graphical user interface, even things like speech-based interface, gesture-based interface. So I think that should be okay. And again, probably check the mark scheme because, they might give you 5 different options here. Right, humans use a denary number system and computers use a binary number system. Explain what is meant by binary number system. Right, so we can say, binary means the number system is base 2. And we can, let's say, this means that only 2 digits are available. Right, this means that only, 2 different digits. And then let's see here in brackets, right, I mean, they're going to be bits in binary's case, are available. And I mean, I guess we can say, usually this is 0 and 1. So let's say, let's say in digital binary systems, the 2 bits available, right, can be thought of as being 0 or 1. Alright, because I mean, obviously, in normal binary there would be 0 and 1, but you could equally have a binary system where, the sort of digits or the bits are A and B, right, or the digits are, 4 and 5. But I guess, in regular binary, of course, just 0 and 1. For part B, it says convert the denary numbers 14, 59 and 234 into binary. And it is a bit strange how they want us to do this, 3 times, right, 3 different questions. Right, so 14 then, there won't be a 128, there won't be a 64, right, there won't be 32, won't be a 16, right, but there will be an 8, right, then there will be a 4, that gives us 12, and then there will be a 2, okay, that should be fine. 59, right, so no 128s, no 64s, right, but there will be a 32, right, and then I guess, there will be a 16, right, this will give us 48. Right, there will then be an 8, so that gives us 56, and then there won't be a 4, but there will be a 2, there will be a 1. And again, we can just add that up to check, right, 32, right, then plus 16 is 48, plus 8 is going to be 56, 58, 59. Right, then this one, this one's much more difficult. So let's go 1, right, so there's 128 plus 64. Right, that's going to be 192. Right, then I guess we want a 32, which gets us to 224. Right, then we just want 12, so that's no 16s, right, but then it's going to be an 8 and a 4. I'm going to check that again, right, so 128 plus 64, right, that's 192. Plus 30, right, 222, 224, 232. Okay, so I think maybe this one. Right, let me just check that again. Right, so 192, 224. Yeah, okay, right, 232 and 234. Right, I think that's correct. And if it's wrong, I'll just go back and check at the end and then, update the video. Right, the next one, so convert the denary numbers, right, 926, 926 and 65 into hexadecimal. Now, I mean, the first one, because if you think we can represent 0 to 15 in hexadecimal, so the first one will just stay as 9. Okay, 9 in denary is also 9 in hexadecimal. But then we want to think about the positional values. So the first one is going to be 16 to the power of 0, right, which are just the ones. Right, the next one is 16 to the power of 1, right, which is the 16 columns. And then the next one, well, 16 to the power of 2, which is 256. And if we look, well, of course, 26, right, I mean, it's going to be somewhere between this. Okay, so that means we need to use this 16 columns. Right, so there's going to be 116. Okay, then there's 10 remaining. So 10 remaining in hex is going to be A. Right, the last one, I think, well, we think 64 is going to be 4 16s. Right, and then there's just going to be 1. Okay, just like this. Yeah, and I mean 65, if you know, this is also big A in ASCII. And then, yeah, I guess in hexadecimal, right, this is also, well, I mean, yeah, this is the ASCII code, right, for big A, but in hexadecimal. Right, convert the positive denary number, right, 123 into 8-bit binary using 2's complement. Okay, so this one we can think, well, if we have 7 ones, then 7 ones is going to be 127. So effectively all we want is, well, 7 ones, but just like accept the 4 position. Right, so that, yeah, there's not going to be the -1 to 8. Right, well, there is 64, there is 32, there is 16, there is 8. Okay, but there won't be 4, right? Then there will be 2, there will be 1. And again, you can check that, but I think that should work. Right, okay, then just binary addition. So let's just write these out. And yeah, let's be careful about, where to put the columns, right? So let's line them up properly. Right, so 1, 1. Okay, alright, so binary addition then. 1 plus 0, that's going to be 1. 1 plus 0, right, that's 1. 0 plus 0, 0. Right, 0 plus 1 is 1. Right, okay, now it's a bit more difficult. So 1 plus 1, well, that's a sum of 0, but a carry of 1. Right, then 1 plus 1 plus 1, okay, that's going to be a sum of 1 and also a carry of 1. Right, then we have 1 plus 0 plus 1. Right, that's going to be a sum of 0 and then a carry of 1. And then, well, yeah, 1, 0, 0, right, that's going to be 1. So I think that should be correct. And I know some people get a bit confused about this because they think, well, like, why does 1 plus 1, why does that kind of equal 0 and then a carry of 1? And the way you can think of it is, well, in binary, 1 plus 1, right, that equals 2. Now, how do we represent in 2 in binary? Okay, we represent 2 in binary as 1, 0. And that's what we've got here, right, because we've got 1 which has moved into sort of this left position, and then we've got the 0 here, which is this. Okay, so our sum is 1, 0, right, which is 2. And then likewise, if we have, say, 1, 1, 1, well, if we add these, right, this is 1 and then carry 1. So if you think, well, what's like 3 in binary? 1 plus 1 plus 1. Oh, right, that's 3. Now 3 in binary is just 1, 1. And again, that's what we've got here, right? This 1 in this position, then also, this 1 in this position. Right, so I think for me, I mean, that explains it, and hopefully that makes sense for you. Right, then a computer has a central processing unit, CPU, circle 3 components that are built into the CPU. Okay, so yeah, this one should be quite easy, if you're familiar with like the fetch-decode-execute cycle, because there will be the accumulator. Okay, that's one of the registers. Right, there will also be the control unit, because the control unit, well, that's kind of the brain of the CPU. That's going to send out the timing signals, right, the system clock. It's also going to decode things, decode instructions. It's also going to manage, for example, like interrupts, right, it's going to handle all of those signals. The graphics card is not, hard drive is not. Okay, motherboard, I mean, the motherboard basically is the, printed circuit board in which all of the other, let's say all of the peripherals are connected to. And also the, for example, the CPU is connected to it, the graphics card, all of the, input, output, right, everything's just connected to the motherboard. Alright, and then while we think, so the program counter, okay, this is also going to be one of the registers. And the program counter, hopefully you remember, but this stores the address of the next instruction we're about to execute. Right, part B, CPU has cache, explain the purpose of the cache. And this one, I do have another picture for this. Alright, so, okay, there we go. Yeah, it's a bit laggy. Right, so we see here then, well, here we've got a picture of our CPU. And in this case, well, I've got, core 1, core 2, core 3, core 4, right, quad core CPU. And we see, right, well, each core is going to have a level 1 cache. And level 1 cache, this will be the smallest cache, but it's going to be the closest, to the actual processing parts in the CPU. So, for example, closest to, the ALU, closest to, the NDR, right, all those critical components. But yeah, it's going to be, it's going to be the closest, right, the fastest, but the most expensive. Right, L2, I mean, this is also fast, it's also close, I guess a little bit cheaper. But yeah, it's also going to be a bigger storage. And then like L3, well, this will be the slowest cache. However, it's going to be the biggest cache, right? And it's also, the furthest. Right, the thing is though, all of the cache, so even L3 is faster than main memory. So yeah, when it says main memory, this just means RAM. And I think a statistic I saw is that L1, right, so the level 1 cache, right, that's going to be, well, let's say 100 times faster than RAM. Right, and then, so yeah, level 1 is 100 times faster than RAM. I think level 2 is about 25 times faster than RAM. Yeah, level 3 maybe 10 times, I'm not sure. But, I mean, the reason that, cache is useful is because, well, this is where the, let's say the frequently used data and instructions will be stored. Because you imagine if, like, every instruction we have to go to main memory, load it from main memory, right, that's going to be slow. Because again, like main memory is a kind of long physical distance. Like when you're talking about doing instructions, 3 billion times a second, right? Like if main memory is, I don't know, like let's say 10 centimeters or 20 centimeters, like from the actual hard drive, 20 centimeters from the CPU, then, actually it does take time for the electrical signals to travel back and forward. Again, when you're doing it like 3 billion times a second. So yeah, that's why, again, right, the frequently used instructions are then going to be stored in the cache, right, and frequently used data. So let's just try and put that into words. Right, so we'll say, the cache, right, is, let's say, fast access memory. You could say, right, small fast access memory. Right, let's say close to the CPU. Right, that stores, let's say, frequently used, right, instructions and data. Right, let's say, this provides the advantage. Or we could say, right, this is useful, or this is, necessary. Let's say this is useful since it means the CPU doesn't have to wait for data to be fetched from the main memory or from RAM every time. Right, doesn't have to wait for, or let's say instructions, and data to be fetched. You could say fetched, or read from, from main memory. Let's put in brackets here RAM. Let's say like each instruction. So I think that's fine. Right, so the CPU has a component that regulates the number of fetch-decode-execute cycles that the CPU can perform in a second. Right, we want to state the name of this component. So what this is saying then is, well, there's one component, and when this kind of, I don't want to say the word, but when this is kind of active, right, then it will actually cause the instruction to execute. And the word, I mean, rather than active, right, we can say when it ticks. So hopefully this should give it away, right? This will just be the system clock. And the way this works is you can think, well, let's say, right, this is the clock signal, right? When the clock signal ticks, okay, so here an instruction will execute. Then it's going to go down. And, let's say, right, the next time it ticks, right, well, then here another instruction will execute. So each time it ticks like this. Right, the CPU has a component that carries out all calculations and logical operators, logical operations. right, and then yeah, state the name. I'm saying calculations, right, you can also call arithmetic. So hopefully you should see, right, arithmetic logic, that's going to be the ALU, and let's also write the full name, right, so the arithmetic, right, and logic unit. Okay, right, an employee uses a web browser on their computer. Describe the main purpose of a web browser. Okay, so I guess we say a web browser is going to be used to, let's say kind of handle the HTTP requests. So a web browser will, send out the, it will send out the HTTP request. Right, the web server will then respond, and then when the web browser gets that response, well, then it will have to render the content, right, and that content will be like HTML, JavaScript, CSS. But it will just have to, take this code, right, take the images, the video, the audio, and just kind of render it into a page that, that obviously the user can see, click on, listen to, depending on what the content is. So let's say that, let's say the web browser, right, is used to, let's say communicate with a web server. Via maybe, let's say, implementation, right, of the HTTP, and let's say HTTP, right, / HTTPS, right, protocols. Okay, so right, I think that's fine. Then we can probably say the browser will send a request, the server will respond. Or let's say when the browser sends a request, let's say it will wait for a response. From the web server. Let's say upon receiving. Upon receiving a response, the browser, okay, let's say it will pass, right, so it will pass the content. So let's say, right, HTML, maybe JavaScript, CSS, let's say etc. I guess you can say, it will pass the content. If it's JavaScript, it also needs to execute. So maybe let's say that, execute the JavaScript. Right, and then we'll just say, and render the, I don't know, maybe let's just say, like, render a visible web page to the user. Let's say that they can interact with. I guess if it's a dynamic website, they can interact with it, right? If it's just a text-based website, I guess they can't really interact. But alright, so the employee wants his payment details to be automatically filled in when he buys products using the internet. Right, identify the function of a web browser that could be used for this purpose. So I think, this is basically saying, well, what can remember his, payment details, right? What could remember his, say, username, right? And for this one, hopefully you remember this will just be a cookie. Alright, so okay, let's be more specific, because you could say session cookie, you can also say persistent cookie, and if here he wants to remember, if he wants it to remember his payment details, and let's assume this is probably across different sessions, right? So maybe he turns off his computer, he logs on the next day, or he opens it the next day, right? He wants it to be remembered, so that's going to be persistent, right? Persistent cookies, because session cookies, well, they're only stored for that session. And when we say session, we mean like while the browser is open, right? As soon as you close the browser, as soon as you turn off the computer, all of those session cookies are going to be deleted. Right, next one, the employee wants to be able to quickly access websites that he regularly uses, right? Identify the function of a web browser that could be used for this purpose. So I think here we can probably just say bookmarks, right? They'll store a list of bookmarks, his favorite websites. Right, the web browser uses the secure socket layer, right, SSL protocol to transmit personal data securely over the internet. Right, state how the SSL protocol secures the data for transmission. Right, here you can just say encryption. Probably again, you probably want to write this as a sentence. So you would just say, well, SSL will, encrypt all of the data traffic, right? Let's say between the client, right, which is going to be, let's say WB, right, web browser, and the web server, right. And again, yeah, just as a full sentence, you say, just explain that as a full sentence, I would say. Right, errors can occur when data is transmitted. Give one reason why an error may occur when data is transmitted. Now, I'll be honest, I didn't actually get this one. I did check in the mark scheme. I probably would have just said, data corruption or, like a hardware error or something. I guess maybe that's not specific enough. So what they're looking for is going to be interference. And interference, I mean, let's say you're using like you're using some like Ethernet cable, or it could be Wi-Fi as well. Now, let's say here you've got, one wire like this, right, then you've got another wire, close by, or I guess if it's Wi-Fi signals, that's going to be maybe even more apparent. Of course here, this is going to have like electrical voltages, right? Now, like maybe this one also has, I want to try and draw them kind of out of sync, or out of phase. Actually they're quite in phase, to be honest. But like obviously, right, if these wires are not properly insulated, right, then the electrical signal from this can interfere with the electrical signal from this, and then you're going to get some wave that's different from the original. Right, some error detection methods use a calculated value to check for errors. Right, tick one box to show which error detection method does not use a calculated value to check for errors. Right, so a check digit, this will use a calculated value, because this can be, for example, like ISBN. Right, also credit card numbers, I think credit card is just the last digit of a credit card, and that uses something called the LUN algorithm. And actually on the Pseudocode website I have this as a challenge, and you might think credit card is going to be super complex, like super secure. Obviously, well, it is secure, but this algorithm is actually super simple, right? It's actually just the same as the ISBN, where you take something like, I don't know, let's imagine we've got say 1 2 3 4, right? This is our ISBN number. I think in reality ISBN they're like 13 digits or something. But what you do is you take the first one and then let's say multiply it by 3, the next one multiplied by 1, the next one multiplied by 3, right, then 1, so it just alternates. So we see, well, 1 times 3 is going to be 3, 2 times 1 is 2, 3 times 3 is 9, right, 4 times 1 is 4. Okay, you then add all of those up, right, so that's going to be 5, 14, 18. And then you just want to think, well, what number, actually I'm not sure exactly, I think it's going to be what number do we need to add to this in order to get it to be a multiple of 10. And in this case, hopefully we can see, well, if we add 2 to it, right, then it's going to become 20. And obviously 20 is a multiple of 10. Right, so in this case that would mean 2 would then be our check digit. And that's just how ISBN and the LUN, right, credit card algorithm, they both work the same. Checksum is basically the same, although the difference with a checksum is, it's not just going to calculate one digit. Maybe it might calculate some 64-bit integer, or it might calculate a string. For example, in the case of hashing algorithms like MD5, also something like SHA-256, right, they're going to calculate a string, right, rather than just a simple integer. Right, so echo check. This one, basically you're going to send the data, let's say the client, and then, let's say the server, right, or the receiver. Maybe let's call it sender receiver. Right, so let's say they send the data ABC, right, the receiver then just sends that data back, okay, they echo it. And then if this guy, let's call them the sender, right, if the sender receives the same data coming back, well, they know that the receiver must have received the correct data, because they've responded with the correct data. But let's say if they return ABD, well, of course in that case, like, possibly the receiver has received the wrong information, because like either there's been some data corruption when the sender was sending it, right, so there could be data corruption here on this outbound journey, right, or there could also be data corruption here on the inbound journey, because like maybe they did receive ABC, but then actually, right, this inbound journey is when it got corrupted to ABD. However, in either case, the client is going to resend, right, or the sender is going to send it again, right, just to be sure that yeah, just to be sure the receiver did get the correct data. So I think here, I mean, this is not using a calculated value because it's just sending the original data. And then a parity check, I mean, let's say we're using even parity. If we have some bits, and I think I'll just use 4 bits, right? Although in reality, you know, maybe it's going to be 7 bits, and then you have like 1 bit for the parity bit. Let's say we're using even parity. Well, we just count how many ones there are. So in this case, right, there's 2 ones. And then if we're using even parity, we want to make sure that the total number of ones is even. So in that case, right, we would keep it at 0 because, yeah, so we have 2 ones, right, which are going to be even. However, if we're doing the same thing, but we're using odd parity, well, here, right, there's 2 ones, but in total, we want there to be an odd number of ones, which means that we have to make the parity bit 1, okay, in order to now have 3 ones, which is odd. So yeah, that's just how all of those work. Right, the next one, so an automatic repeat request, or ARC, can be used to make sure that data is received free of errors. Right, it can use a positive or negative acknowledgement method to do this. Right, explain how ARC operates using a positive acknowledgement method. Alright, so this one is a bit more tricky. Yeah, let's try and do this. So again, we've got a sender, right, then we've got a receiver. Now what's going to happen? Well, again, the sender is just going to send the data. Right, they're then going to wait for the receiver to kind of acknowledge if they got the data. So the receiver will just, well, I mean, yeah, if the receiver receives it, okay, then they'll just acknowledge. So let's just say, yeah, ACK, right, an acknowledgement. Right, if the sender receives this acknowledgement, well, then they know, you know, the data has been received correctly. Okay, so that's fine. And I think there's another thing, they call it the right, the cyclic redundancy check, right, CRC. And I mean, this is even more simple than the parity check, where basically, you know, you take your stream of, you know, bits. So let's say this, and then you literally just count how many ones there are. So in this case, there would be 3. Right. So here, well, basically, you just send this 3 like as an additional thing. Right. So I mean, well, you think, right, you would send the data, right, and then you'd also send the CRC at the end. Okay, and obviously, well, the receiver can then check. They can then perform their own check and obviously check that you know, the data matches you know, this CRC that you've provided. So let's assume it doesn't match. So maybe a CRC error. And in fact, let me use a different color for this because these are all going to be distinct. Right. So this is okay. I mean, all right. Yeah, this is situation 1. Okay, which is kind of successful. And I think there's sort of 3 situations. Yeah, let me use a different color. Right, so in this case, well, again, they just send the data. But let's say there's been some, you know, problem, right? This CRC is incorrect. So then what's going to happen? Well, they're then going to give a negative acknowledgement, you know, just saying, well, hey, the CRC value is wrong. It doesn't match the data you sent. Right, and then, of course, well, in this case, the client, the server, okay, sorry, right, the sender can then send it again. And obviously, well, if there's another mistake, it's then going to send another, you know, negative acknowledgement. Of course, right, if there's no mistake, well, then it's going to respond, right, just with a positive acknowledgement. And, you know, this process will continue maybe like 3 times. So if they have a mistake, you know, if like every time there's a mistake, right, if you get to the maximum number of tries, okay, then it's just going to stop. Because let's say you have some network error, or yeah, you have some, you know, hardware error that's causing the data to, you know, constantly become corrupted. Well, you wouldn't want to like infinitely be sending data because that's just going to slow down your network. Yeah, you know, it's just going to cause all kinds of problems. Right, and then let's say the sort of last case, maybe let's use I don't know, this. Yeah, let's use green. Although this is also going to be a failure case. All right, let's imagine they send it. But for some reason, you know, yeah, let's say there's some, you know, network error, right? This receiver, they don't actually receive it. So in this case, the receiver is not going to send anything because, like, they literally don't know that someone's trying to contact them. So what's going to happen, right? The sender here, they're then going to wait a given amount of time. So let's say this is like 3 seconds, and if they haven't received anything after 3 seconds, well, then they're going to try again. Right, if that, you know, if obviously it doesn't work again, right, then they're going to wait another 3 seconds, right, let's say try again. And they're going to keep doing this until they kind of exhaust all of their tries. Right, so you can say maybe the sender should try 5 times. and if after 5 times they still haven't got a positive acknowledgement, well, then they're going to stop. For the same reason as this, right? You don't want to sort of infinitely be sending data, filling up the network. And of course, I don't know, like let's say on this number 3, well, let's say they do receive it. Then of course, again, they're just going to send back the positive acknowledgement. And obviously, here it's going to be successful. So I think, basically we just want to describe this, and this is going to be 5 marks. And I think, the difficult thing is always actually putting it into words. Right, so I think we can say, maybe the sender will send the data along with a CRC. We could say data or, payload. Right, let's say along with a... and you could say checksum because, maybe they might send a checksum. But let's say, maybe along with an error detection method. Right, let's say, e.g., right, cyclic redundancy check. I'm not going to worry about spelling now. Right, the sender will send the data, along with an error detection method, e.g. cyclic redundancy check. Okay, let's say, right, if the receiver receives it, right, if the receiver receives the data, they will also do the same calculation. Let's say the same error detection calculation, right, and check. And check maybe the integrity of the data, or I don't know, maybe and check the result matches. What was sent by the sender. Right, let's say if it does. Right, then right, let's say a positive acknowledgement. So that's going to be the ACK. Right, will be let's say sent back to the sender. Let's say, right, who will now know the transmission was successful. Let's say who will hence know the transmission, right, was successful. Okay, right, let's say, and I think here we can kind of combine the error situations into one. So let's say, right, if the cyclic redundancy check, let's say if the error check was maybe invalid. Or let's say the error check calculation, gave a different result. Right, the receiver will send a negative acknowledgement. Right, acknowledgement, and the sender will resend. Right, I think then we can say, so if we then talk about number 2, right, if we talk about number 3, we can say if the receiver doesn't receive the data. Right, if the receiver doesn't receive the data, right, let's say the sender will never get a response, right, or never get an acknowledgement. Right, okay, let's say, they will wait a given amount of time. Or let's say in brackets that's going to be called the timeout. Right, let's say, after this timeout they will then send again. Right, and then we can say, like, if they still don't get a positive acknowledgement, then they'll keep, so let's say they will keep resending until they get a positive acknowledgement, or until they exceed their number of tries. Right, they will keep resending, right, until they get a, let's say until they get a positive acknowledgement. Right, or until they exceed the, I guess let's say maximum number of tries. So I think that should be okay. Question 6 says, a company uses cloud storage to store its data. Take one box to show which is not a characteristic of cloud storage. Right, so data is accessed through a network. Well, this is true because, let's say you're in your home or school or office, right? Of course, well, yeah, you're then, using the internet, to access the cloud servers in a different physical location. Right, data is stored locally. Well, this is going to be false, okay, because again, it's in a different location. And yeah, different location, well, this means, it's stored remotely, right? That's the same. And yeah, physical servers are used to store data. Well, this is true because, even though it's called cloud, like it's literally just, I would say it's just kind of like mostly a marketing scheme really. Because, just like 20 years ago, people were using like physical servers to, store data, store websites. A cloud is just the exact same thing. Although it does offer advantages, kind of like auto scaling. So yeah, like if your website becomes super big, right? Most cloud providers will be able to like automatically scale your website, by allocating more hardware, for example. Although yeah, you will pay like maybe 10 or even 1,000 times more by using the cloud than you would if you were just using, for example, like a simple VPS or even self-hosting, which would be even cheaper. Right, so explain 2 advantages for the owners of the company of storing its data in cloud storage. Right, so I think the first one you say, let's say employees, can access the data from anywhere at any time. Data, anywhere / anytime. We can just say like high availability, okay, because that's really what this means. Like availability is kind of how often, where you can access the data, right, things like that. Right, so another advantage, you can probably just say backup. So yeah, let's say cloud servers, right, can be used as a remote backup. And the reason it's good to have both a local backup and remote backup, well, I guess you want a local backup because like let's say if there's a problem with the cloud server, right, at least you've got a local backup that you can easily use, right? Hopefully it's safe in your own office. But at the same time, you don't just want to have a local backup because let's say there's a fire, right, or a flood. Or even even like a robbery, right? Someone breaks in, they steals all your stuff. If you've only got a local backup, well, all of that is going to be destroyed or stolen, right? So that's why it's good to have 2 locations, and it's often good for those locations to be quite physically distant, because let's say if I don't know, maybe if you've got a cloud like in the same country or the same. Like same city, well, there could be some natural disaster that affects the whole country, or if it's some political issue, right, maybe maybe the government sort of shuts down all of these cloud providers, and then in that case, right, if they shut down that cloud provider in your country, then obviously, well, you've lost all of your data. So yeah, that's why it's good to have sort of redundant copies, right, in different physical locations. Although again, of course, that is going to be expensive. Right, so then we want to explain one disadvantage to employees of the company of storing data in the cloud. And this one's a bit strange because if you just have one disadvantage like for the company, well, you could say it's going to be expensive. But yeah, if you're talking about employees, you can probably just say it's slower, right? So it's going to be slower than having it stored locally. So let's say slower to, well, let's say less sort of access, right? Or you can really just say download/upload, right, compared to locally stored files. Yeah, so I think that's what I say, and I did also check the mark scheme for this. They also give this strange answer where they say that if things are stored on the cloud, then, well, because here we said that employees can access the data anywhere, anytime. Right, this means that the boss might then, let's say they have a problem at like 2 a.m. in the morning, the boss can literally call them up, and he can be like, well, hey, you can access the cloud, you can access the files, you should log in and fix it at like 2 a.m. in the morning. Whereas of course, like if for example they had to drive into the office, yeah, maybe the boss would be less kind of, less demanding that they fix it. Whereas yeah, here, like even if you're on holiday, even if it's the weekend, whatever, right, you can access it. So possibly the boss might be more demanding. Question 7 says a photographer takes an image with a digital camera. The photographer sets the resolution and color depth for the image. Right, we want to state what is meant by the image resolution. So the resolution, you can think of it like if here we just got, well, width and height. Right, well, the resolution is just the number of pixels. Right, and the number of pixels is, well, the width multiplied by the height. Because if we've got, let's say, a width of 1,000 and a height of 500, well, if we multiply these together, right, that's going to be how many pixels? So let's just say that right, it's going to be the let's say the amount of pixels. Right, amount of pixels in an image. And you can probably mention the dimensions too. Let's say calculated by right, by the width times height. Or well, let's say right, W times H, yeah, width times height. Of course, in the exam, write down the full words. Right, state what is meant by the image color depth. Right, so the color depth, I mean, this is just how many bits per pixel are used. Well, just how many bits are stored per pixel. So let's say, right, the number. Okay, well, that should be number, right, of bits. Yeah, used to store each pixel. And to give an example, well, let's say we use a color depth of 3, right? That means we have 2 to the power of 3 different colors, right? So here we can only represent 8 different colors. Now, I think a typical color depth is going to be 2 to the power of 24, right? So yeah, 24 is the color depth. And this one, I think this gives us about 16 million, right? Yeah, 16 point something million, because yeah, this is a typical value. Right, and I think on old screens it would often tell you, like it would say, do you want to use like 16-bit color, 24-bit color, maybe 32-bit color, and yeah, it was always going to be like 16 million something different colors. Right, so give one benefit of increasing the color depth of the image. Well, like we saw, if we have 3, color depth of 3, right, we only have 8 different colors. Right, 24, we have 16 million. So let's say well, and again, write in full sentences, but I'll just say, like more colors. Let's say more colors can be represented. I think that's pretty much a full sentence anyway. In the image. Right, then we want to say the photographer, the photographer compresses the image using a method that permanently reduces the color depth and resolution of the image. Identify which compression method the photographer uses. Right, so here then this is going to be lossy because it's permanent, permanently reduces. Whereas obviously lossless, well, we can decompress and get the original again. Right, one benefit for compressing is reducing the storage space it uses. Give 2 other benefits of compressing the image. Right, so let's say faster to send. Or faster to transfer. Let's give examples, right? E.g., over internet, USB. Alright, something like that. And I think similar to this, you can also mention, right, uses less bandwidth. Because again, it's faster to send because there's less bandwidth basically. Because the file size is smaller. Right, the next one, I think they often mention about, let's say for example email, they often have a file size limit or attachment limit like 25 megabytes. And maybe if, I don't know, like if you were sending lots of images, or if you had one massive, you know, like 10,000 by 10,000, you know, 32-bit image or something, right? Maybe that's going to be over the file limit. So let's just say maybe allows. Yeah, maybe allows us to bypass or to, you know, be under. Let's say, yeah, be under the file size limit. Right, yeah, let's say like e.g. I don't know, like email attachment limit or something. Yeah, and of course, you know, this could be like some social media app as well. They might have some limit. Right, so then draw an annotated diagram to represent the role of a router. Right, so I mean this one I could just draw. So let's just say here, you know, you have a client, right? Then you have a server, or again, you know, you can call this sender and receiver. That's also fine. Now the router, let's have one router here, maybe another here, you know, another here, right, another here. So let's say the client, you know, maybe first they send to this router. Okay, this router then sends to this router. Maybe this one sends to this one, right? This one sends to this one. And the way they'll do that, I mean, let's call it maybe routing table. Yeah, all right, so let's say routing table. And I mean, well, let's say maybe yeah, each router, right? Each router has a routing table, right, which is used, to determine the next hop. Right, next hop. Okay, and the thing that's good about you know, packet switching is that, let's say for example, I don't know, maybe this router stops working, or yeah, I don't know, maybe there's some problem with, you know, this like fiber optic cable or something. Well, then we can have it where maybe now it might send to this router, but you know, this router knows this is not available, right? So it's then going to send to this one, and yeah, maybe this one sends to this one, right? And then obviously here. So let's say we have, I don't know, maybe like route 1, and let's say, you know, route 2. Yeah, and I think you could describe this as by saying, you know, there's kind of, yeah, packets can be sent along alternate routes, right? And that's probably a good thing to mention. Yeah, so we can say the packets are sent along here, right? And I do actually have just a little bit more detail. So, I mean, we can see here this same kind of diagram. And let's imagine we want to send, okay, here's the pen. Let's imagine we want to send from, maybe, right, so device, well, 12001. And let's say that 12001 is going to be this, or yeah, this one here. And I don't know, we want to send to, you know, 14, right, 001. Or in fact, I mean, let's call it 2 actually. Because in many cases, you know, number 1 is going to be the router, right, or the switch. Okay, so if we look here then, well, if we're in this network, okay, yeah, sorry, let's not look at that. Right, yeah, because here we want to send to 14. So from 14 it's saying, well, send to router 1. Okay, and again we see this is the routing table. Right, so we send to router 1, okay, which is going to be this one. Now when we get to router 1, well, it then looks in its routing table. And then here it says, well, right, 14, we want to send to this R4. Of course, yeah, then, so we think, I mean, basically it's been sent from this computer, right, to this switch. The switch then sends it to this router. Yeah, this router then sends it here to router 1. And then we see here, well, yeah, this router then sends it here to router 4. Right, if we see here, we're going to, you know, 14, well, then direct. So I guess this means it's in this network already. Right, so of course, well, then it can send it to the switch, and I mean, let's say this one here, right, and then it's just going to send it to this device. So yeah, that's kind of how routers are going to work, right? They're going to use the routing table in order to determine, you know, which router to send it to next, right, or yeah, what the next hop is going to be. Right, computer has secondary storage. The table contains statements about secondary storage. Complete the table by writing the type of secondary storage. Okay, right, some may be used more than once. right? So data is stored using pits and lands. Okay, so pits and lands, and I feel some people might have skipped this because, I mean, I know now they've said that you don't need to know kind of how these hardware work in detail, but obviously you do still need to know the basics, right? You know, according to these questions. Right, so pits and lands, you think, well, it's going to be a surface like this, and I don't remember exactly how it works, but I think what it is that if there's a change, like maybe a change means, for example, a 1. So for example here, right, here it changes, so it's going to be a 1, but then any time it stays the same, it's going to be a 0. And then, you know, when there's a change, so here it goes up from a land to a pit, right? And I mean, when we say a land, well, a land is going to be this high ground, okay, the high thing, right? A pit, that's going to be the low one. And I mean, yeah, hopefully you know what land and pit means, you know, just kind of like in English. I mean, pit just means like hole in the ground, basically. Yeah, I mean, so basically you say, well, you know, a land corresponds to something, a pit corresponds to something. And I think really it's actually based on the change, right? It's not as simple as saying, well, a pit is 0 and a land is 1, right? It's actually based on when it changes. But anyway, yeah, so I mean, this one then, right, this is going to be optical storage, right? So let's just say optical. And when we say optical, well, that means, right, well, light, right? So CDs, DVDs, Blu-rays. And I think actually, well, yeah, using a laser, right, which is, yeah. So I mean, here we can also write optical as well. Because I mean, the way this is going to work is, well, you're going to have a laser. So let's say here, this is like the laser beam. Well, so yeah, well, you have the emitter, right? Then you have a sensor. And of course, this laser beam is then going to be, I mean, I think we say, well, if it's a land, it will be reflected. Okay, if it's a pit, it won't be reflected. And then obviously, yeah, based on whether this receives it or not, okay, then it will know, you know, if it's yeah, if it's shone onto a land or if it's shone like into a pit. Right, the next one, data is stored using control gates and floating gates. So yeah, this one was in, I think, paper 12 or maybe paper 11. So here what we said is, let's say you have a control gate, let's just say C, right? Then you have the floating gate, let's call that F. Now, and I mean, let's just sort of contain this in here, like something like that. Now the floating gate is then going to contain the electrons. I guess that should be, yeah, E minus, right? Okay, E minus. So if the control gate is closed, well, then it means the electrons will stay in this floating gate. However, if you turn the control gate on, okay, which, well, on I think just means open. So if the control gate is open, well, then it means that either electrons can leave the floating gate, yeah, or new electrons can come into the floating gate. And probably what it is that maybe if there are electrons, maybe that means a binary of 1, and maybe if there's no electrons, it might be 0. You know, possibly it's the other way around, but yeah, the general idea is obviously, yeah, if there are electrons or if there's not electrons, one of them is a 0, one of them is a 1. Right, so I mean, this is going to be, well, for example, like NAND, SSD. So let's just say solid state. Yeah, solid state storage. Right, next one, data is stored using electromagnets. Well, this is then going to be magnetic storage. And if you think about a hard drive, well, a hard drive, you're going to have the platter. Right, so the platter is just the disk. Of course, right, this disk is going to be spinning. And then you're going to have a read-write head. So that read-write head, let's just do it here. Right, this is going to be attached. Yeah, I'm not really sure how to draw this, but let's say this is attached to an actuator arm. Right, the actuator arm can then, you know, move it across the disk, right, or move it across the platter. And obviously, well, based on the magnetism, you know, of these, yeah, well, based on, you know, the magnetism of the hard drive, again, that's going to correspond to a 0 or 1. I think, yeah, based on the polarity, like if it's north or south. So that's going to be this last one then, right? Data is stored on a platter that's divided into tracks and sectors. And basically, where you think a sector, because it's just a circle, right, with a center. So a sector is just going to be like this. Yeah, or I think actually, so a sector would actually just be, for example, so this blue one here, right? And then a track, well, a track is actually going to be the kind of the whole thing all the way around. Right, so let's say, yeah, this kind of dotted one, right, this would be a track. And then if we just say one sector, well, a sector is then going to be part of a track. And of course, they're going to store different amounts of data, right? Like maybe, I don't know, maybe a sector stores, 1 kilobyte of data, or, 1 kibibyte of data, for example. Yeah, so this is then just going to be magnetic. Right, so two differences between primary storage and secondary storage. Okay, so I think one, we can say primary storage can be directly accessed by the CPU. So I'm just going to say, right, PS, yeah, directly right, accessed by CPU. So this means, if you want to read data from primary storage, well, the CPU can do it directly. Whereas, for example, let's say, well, secondary storage or SS, let's say, right, data right, has to go through primary storage, right, before it can be used by the CPU. Yeah, so let's say, right, loaded into PS. Right, so yeah, loaded into primary storage, right, before usage by CPU. Oh yeah, before it can be used by CPU. Right, then two other differences, and these are a bit tricky because, for example, like, I mean, some primary storage will be volatile, some will be non-volatile, whereas secondary storage, I mean, basically it's all non-volatile. And I mean, to recap, I mean, volatile means when you turn off the power, the data is lost. So something like RAM, okay, that will be volatile, whereas ROM, well, ROM won't be volatile because you turn off the power, okay, and the data stays on ROM. Likewise for something like a hard drive, right, and SSD, USB, okay, so yeah, all of these are going to be non-volatile, because again, obviously you don't want to turn off the power and like all of your data is lost from your SSD or hard drive. So I think we can probably say this, although it's not really the best because it's not it's not a perfect split, right? Like, for example, we have some primary storage that's some primary storage that's volatile, and yes, some primary storage that's non-volatile. Yeah, but I did check this in the mark scheme, and they also talk about other generalizations. They say primary storage is generally faster. Okay, primary storage is generally more expensive. So this one is a bit weird because, I mean, like, this one is always true, whereas, yeah, if we say, let's say, right, PS, right, is sometimes, right, sometimes volatile, yeah, and, well, sometimes, right, non-volatile. Let's say secondary storage, yeah, is, I mean, I think always, yeah, I mean, let's say, yeah, always non-volatile. I mean, I can't think of an example that's not. Likewise, you can say again, PS is generally more expensive, but generally faster. And I guess you can also say secondary storage is, generally bigger, at least with SSDs and hard drives. Now, something like a USB, not so much, because maybe you have 16 gigabytes of RAM, but you might only have a 4 gigabyte USB. Yeah, although I think these days USBs have also got pretty big. Right, next one. So a car repair garage uses an expert system. Complete the description about the operation of an expert system. Right, okay. So I do actually have another picture for this just to explain how it works. And again, this was also in the previous paper. But we say, well, we've got this human here, right? So yeah, this guy, right? He'll then, well, yeah, he's then going to use a user interface. Again, could be command line interface, graphical user interface. Yeah, speech, gesture, anything. He's going to use this to interact with the expert system. Now, let's say the inputs that he gives, well, this is going to be used by this inference engine, right? The inference engine then has a knowledge base, and the knowledge base will just be a list of facts. So quickly, just going over the same example, I think I've done this, maybe twice already. But let's say, for example, you have a dog. You have a list of facts about the dog, like it has 4 legs, it's a mammal, yeah, maybe it can't fly, it has hair, fur, right? Then you have a list of rules, right? So the rules will be in the rules base, and they'll say, well, if the animal is a mammal, and Yeah, and has fur. Yeah, and has four legs. You know, and can swim. Right, you know, yeah, and. Right, you know, then we say it's a dog. Right, of course. Whereas if we say, well, yeah, if it's, I don't know, maybe if it can swim, like if it, yeah, I think if it can swim, if it doesn't have bones, if it has a sort of fin, right, then we can say it's going to be a shark. And of course, yeah, it's going to be more detailed, right? They're going to have more rules than just that. So yeah, we say the inference engine will use the rules base and the knowledge base in order to, you know, kind of arrive at the correct result. Okay, then we can also have an explanation system, and this will explain why it thinks, you know, this is the correct answer. And again, I mean, it can explain, you know, based on this rules base, because we say, well, we think this is a dog, you know, because it has four legs, because it like can't swim, because it has hair, yeah, or fur, right, etc. And then it can also give a degree of certainty. So it can say, yeah, I'm 90% sure this is a dog, right, or yeah, I'm 99% sure this email is spam. Right, an expert system has a something that contains a list of facts. So the list of facts, well, that was just going to be the knowledge base, which is, yeah, going to be this one here. Right, the something applies the something, right, to the something to reach a diagnosis for the repair of the car. So remember, I mean, the inference engine, let's just go IE, right, so the inference engine, this is the one that's using the knowledge base and the rules base, yeah, in order to, you know, arrive at the conclusion, the diagnosis. So again, that's going to apply the rule base, right, to the knowledge base. Because, well, yeah, again, the rules can be, well, does it have four legs? And then, you know, the knowledge base is going to be, well, a dog has four legs, you know, a cat has four legs. Right, the user provides data to the system using, right, and that's going to be the interface. Yeah, okay, interface. Because, of course, well, an interface, right, that's for input of data, right, and also output, so showing the data to the user. Right, expert system has machine learning capabilities. What is meant by machine learning? Right, so again, I'm just going to bullet point, but in the exam, okay, write full sentences. Right, so I think one usually they accept is, well, it's a system that learns. Right, so system learns, or yeah, maybe yeah, it's a system. Yeah, I think saying system is okay. Right, a system that learns. Right, so we say, yeah, performance improves over time. Yeah, maybe improves or becomes more accurate. Right, and then probably you can talk about, I mean, there's going to be either supervised or unsupervised. So let's say for supervised, well, here then we say a user would provide labeled data, or, you know, the trainer, right, the person. Yeah, user provides labeled data. Right, in order, well, let's say, yeah, to train the machine learning model. Let's say to train, let's say ML, right, machine learning model. Yeah, okay, and then let's say, or let's say once trained. Right, yeah, this model. And let's say can, yeah, well, we can say obviously can be used to kind of draw conclusions about unseen data. Yeah, I say, yeah, can be used. Right, to, okay, hang, right, to make predictions about unseen data. Alright, and then let's say if we go unsupervised. So here, I mean, let's just say, you know, massive amounts of data. Right, massive amounts of data, right, are given, let's say given to, you know, machine learning algorithms. Yeah, which, you know, automatically create the model. Right, let's say, yeah, automatically create machine learning model. And I mean, you know, really these algorithms, right, they're just, you know, a lot of the time it's just about like finding, you know, lines of best fit. So if we have some data like this, maybe one data here, 1 point here, 1 point here, 1 point here, 1 point here, well, we can say generally a line of best fit is going to be something like this. So yeah, I mean, that's kind of what this machine learning algorithm would do. Now, you know, this is in 2 dimensions, but you might have a case where you have like hundreds of different data points or kind of hundreds of different characteristics. And, you know, you would want to be plotting some crazy, you know, like sort of 100 dimensional, you know, kind of like path right through the data. So yeah, obviously, I mean, it does get more complex rather than just simple like 2D kind of predictions like this. Right, so we say it learns it's supervised, yeah, unsupervised. And then, I mean, maybe we can say, right, it's often going to have, you know, performance that maybe exceeds humans. Yeah, I mean, or maybe we can talk about the speed. Let's say, right, speed, yeah, and accuracy. Right, yeah, may exceed that of humans. Yeah, let's just say may exceed humans. Alright, and then I think, yeah, okay, that's it. Alright guys, so again, I mean, hopefully this video is useful, and as always, I mean, check the mark scheme as well, because they're going to have more answers than what I gave. But yeah, hopefully it is useful to actually have, you know, someone kind of explaining the thought process, yeah, rather than just seeing the answers in the mark scheme. Right, and well, if it is, then I'll see you again in the next video.